Okay, let me give a short review of where we were before. Okay, so we were discussing SU2, the matrix group SU2, and it can be thought of as the group that preserves the norm of a two-component complex wave function. Okay, and so if I have a wave function like that, so which is a wave function, say, for a particle like an electron, so I can make a linear transformation on this. So psi goes to u of psi. Let's call this new wave function psi prime. Then if I say psi prime, psi, so this is the norm, right? This is going to be the norm squared. So if I say that this, what are the transformation under which this is invariant? Of course, this is psi dagger, u of psi. So if this is going to be equal to psi dagger of psi, which is of course the norm squared of psi squared, then we must have that u dagger u is 1. In other words, we say that u dagger is inverse of u inverse. U dagger is equal to the inverse of u. So such matrices form a group called U2. So U stands for unitary. Okay, and 2 stands for, it's a 2 by 2 matrix. Okay, is this clear?
Yes, sir.
But in quantum mechanics, we have a subtlety, and the subtlety is that if I have a wave function like that, and I have another wave function which is different from this wave function up to a constant phase factor, physically they mean the same thing. So in quantum mechanics, we identify such wave functions. So because this is a constant phase factor, it does not change the normalization. So there is this redundancy in the description of a quantum state. On the other hand, a unitary matrix in U2 can be written in terms of e to the power I, some phase, say, call it I capital phi, I'm using a different notation here, times V. So where V is an element of SU2 and EI of phi is an element of U1. Okay, so we can use the fact that our state has a redundancy in terms of a phase factor multiplying it. We can choose this phase factor to set this matrix, this part of the U2 matrix to 1. Okay, so the relevant part, the part of U that acts, say, non-trivially on the wave function psi is V, which is an element of SU2. So where S stands for the determinant of the matrix being 1. Okay, so if I took, say, U, which was an element of, say, U2, and I say the determinant of U, then we'll have determinant of EI phi times determinant of V. And then this will give me e to the power 2I phi, right? Times 1. Okay? So what we are saying is that we are using up our freedom to set this thing equals to, set phi, this phi equals to 0. So this is
will the determinant of the phase be the phase itself?
So yeah, this is just a phase times an identity matrix, right?
Oh, okay, it's a 2 times 2. Okay.
Yeah. So yeah, I think that's correct. Yeah. So anyway, what I wanted to show is that the relevant group is SU2. Okay. So now in the previous lecture, we showed that if I write U, so now I'm going to use U as an element of SU2, not V. U is my element of SU2. And in a previous lecture, we showed that suppose I write U in terms of 4 complex number, alpha, beta, gamma, delta. And then U inverse is going to be just using the formula for the inverse of a matrix, and the fact that the determinant of U is 1 is delta minus beta minus gamma alpha. Okay. So U inverse is equal to U dagger. So U dagger, on the other hand, is alpha star, gamma star, beta star, delta star. Okay, so if I look at this equation, then I can set alpha star equal to delta and gamma star equal to minus beta. Okay, if I do this, then I can whittle down the number of parameters from 8 to 4. So I can write U as alpha beta minus beta star alpha star. Okay, so we still are missing one condition. We haven't imposed the condition determinant of U equals to 1. So if I say determinant U equals to 1, then that equation in terms of alpha and beta becomes mod of alpha squared plus mod of beta squared is equals to 1. And alpha, I can write this in terms of 2 real numbers. Alpha is, say, x1 plus ix2, and beta as x3 plus I of x4. So here, all the xi's are real numbers. Then this equation, the determinant equation, just becomes x1 squared plus x2 squared plus x3 squared plus x4 squared equals to 1. And compare this to the equation x1 squared plus x2 squared equals to 1. So the second equation, what shape does this describe?
S1.
S1, okay, a circle, a one-dimensional circle, right? Also known as S1. So analogously, this equation then describes a three-dimensional sphere, right? S3. Okay, incidentally, does anyone know what an S0 is? What a zero-dimensional circle is?
Point in the center.
Sorry?
No, it should be a line of unit dimension, -1 to 1.
No, it's actually 2 points,
Oh, yeah.
right? So it means, so it's 2 points. It's a disconnected, it's not a connected space. Anyway, that's something separate. Okay, so we have shown that SU2 is a 3-dimensional sphere. Okay. The other thing we know is that the determinant of U is 1. So if I write U as e to the power I alpha dot, say, t, so then what does it mean for the t's? That means that the t's are traceless, right? From our formula that determinant of U is equal to e to the power trace of I times alpha dot t. And this thing is 1. That means that trace of I alpha dot t is 0. And that means that alpha A, let me call it A, trace of TA is 0. But these are arbitrary parameters. That means that trace of TA is 0. So we see that the generators of SU2 are traceless 2x2 matrices. Okay. The other thing we can show is that, so if U is e to the power plus I alpha dot t, then U inverse must be e to the power minus alpha dot t, right? Because if this matrix and this matrix is the same, then we can write U inverse of U e to the power minus alpha dot t times e to the power plus I alpha dot t. And because they're the same matrices, we can write this as minus alpha dot t plus I alpha dot t, right? And therefore, this is 1. Similarly, U inverse is also 1, right? So we see that U inverse has this form. So the difference between U and U inverse, that this sign is different. But we also know that U inverse is the same thing as U dagger. So what is U dagger? If I go from here to here, now this is basically a series expansion. So this is going to be, the I becomes minus I because it's just a number. Alpha is a set of 3 real numbers, so that doesn't change. T is a set of 3 matrices. They become conjugated, right? Hermitian conjugated. So now U inverse must be equal to U dagger. So if I compare this thing with this thing, we see that T, the generators must be Hermitian matrices. Okay.
Sir, can any element of SU2 be necessarily represented as this imaginary exponential of a Hermitian matrix?
Yes, because SU2 is a connected group. Yeah, it doesn't have those reflections and stuff like that. Okay.
Yes, sir.
So now, so what are these T's? So again, the generators TA, they are number one, 2 by 2 permission matrices. And number two is that they're traceless.